In this tutorial, I'm just going to show you what we are going to do with SuperproDesign software. So I'm going to show you one exercise like how to use the software, how the graphical user interface will look like, and what are the components that we can drag and drop on the software window, and then what are the operations that we can perform using this SuperproDesign software, and what type of charts it can create once we develop some process flow sheet. So that's the purpose of this tutorial. So what I'm going to do is like I'm going to take the example which is already existing in the SuperproDesign software tutorial book. So I'm going to solve that tutorial step by step. I will, before touching the software window, I will just explain it on the paper and using paper and pen. Like I will state what's the problem and how we are going to design that problem in using SuperproDesign software. Yep. So this tutorial is not to make you like full expert in the software, but through this module what you are going to get is like more like an exposure to the software, and if there is some problem, how to deal with that problem using the software. Obviously the software, it will take at least few years to get full expertise, like okay, if expertise, especially if we encountered some problem, if something is not working, then we need expertise. Yeah, so following a tutorial, doing a job is very easy. That's what I'm going to do. I'm going to do the easy one and you are going to do the toughest one. I'm going to give you some project. You have to solve them using SuperproDesign software. Yeah? It's not tough. Just to follow the, I will explain first the tutorial what we are going to do, and then you have to do something similar. So I will give you some case studies. You can download them from the SuperproDesign software's tutorial folder. I think tutorial folder or example folder, I guess. So you have to get the flow sheet and try to play with the flow sheet and try to play with the numbers there, and then at the end you have to generate some Gantt chart for me. So we will see what do I mean by Gantt chart. So I will explain what we are going to do today. So let's start. First I will state what's the problem. So what we're going for to do today is like we will take a batch reactor. Just assume we have some jacket to control the temperature inside the reactor, and then this is it has some overhead stirrer, so which means the stirrer is going to mix the things up. And what we are going to do is like we are going to add two components. One is your A, another is your B. So we are going to put two components, and then we are going to take our product from the batch reactor, and then what we are going to do is like we are going to add some solvent. In this case we are going to add heptane solvent. So in this case A and B, we don't know what type of chemical it is. For the moment, let's assume they are some hypothetical materials, hypothetical chemical or molecules, A and B, but we will define a molecular weight for these two components. So we will tell I have two components that have some specific molecular weight, and then heptane is going to be my solvent, and then when A and B will give rise to a new product called C, and the C will be something in solid form. So we have to separate. So this product will contain your product C plus your solvent and possibly some A and B. So what we are going to do is like we are going to filter them. We are going to filter them using a plate and frame filter. Yeah. hope you all know what is a plate and frame filter. So plate and frame filter is like you will have something like a frame, and then where you will covered with some cloth, and then you arrange this type of setup like a frame with some filtering cloth in series, yeah? Like one filter, second, third, fourth, something like that. It will make like a box, so that you will put your feed solution, so the cloth will filter your solid, and then your filtrate will come this side. So that's how the plate and frame filter will will works, or how it looks like. So so you will take some filtrate, and then we will also remove the cake, filter cake, which is deposited on the plate and frame filter. So we will take the cake out, and then we will also try to wash the cake using some solvent. In this case we can use again heptane as the wash liquid. So we will clean the cake with some wash liquid, and then with some washing solvent, and then we will also take the wash liquid out. We will also take the wash liquid out, and then what happening inside the batch reactor is like we are performing a stoichiometric reaction, and the reaction goes like this. So this is a forward reaction. So 1 mole of A and 1 mole of B reacts with 1 mole of B to give 1 mole of C. So that's the stoichiometric reaction. So we know the like 1 mole of A, all are in molar compositions, 1 mole of B give rise to 1 mole of C. So these are some other conditions. What else? And then since heptane is like a volatile liquid, so we will put a vent in the reactor. So what we are going to say is like we are going to remove the heptane vapors generated due to mixing and also due to some temperature. So we will create a vent to remove the gas out, heptane gas out, and then we will perform this stoichiometric reaction at 50 degrees centigrade. So we are going to heat the solution to 50 degree centigrade. And what else we have to remember? Let me check the notes, what we need to do. Yes, and a few more things. So this hypothetical material like A, B. So this hypothetical material A, for the moment we are going to when we start the problem, we will start that A contains the physical properties of sucrose, but we will change the molecular weight to 150. So which means it is just a hypothetical material, but it have other properties of sucrose, probably the same density. And then it will be like in solid form. We need to precipitate something. So this is a hypothetical material. So we will drag and drop this some material that has the properties of sucrose, and then we will change the molecular weight to 150. Of course, the molecular weight of sucrose is something else, definitely not 150. And then we will do the same for B. We will drag and drop the properties of water, and then we will change the molecular weight. We know the molecular weight of water is 18, but we will change the molecular weight to 25. So both will be something like a hypothetical chemical. And then C will be the same. So we will create some new chemical compound, and then we will call it as C, and then the molecular weight of this compound is going to be 175. So this is not wonder if you have a stoichiometric reaction 1 plus 1 plus 1. Let me change the color. So you see like 1 mole of A, 1 mole of B, 1 mole of C. So obviously this is correct. You have 150 molecular weight of sucrose, 25 molecular weight of 150 molecular weight of compound A, and 25 is the molecular weight of compound C. They both combine to form that should be equal to 1 exactly the molecular weight of this plus this, 150 plus 25. Yeah, so that's the meaning of this type of reaction, stoichiometric reaction. So it will be 175. I hope you all studied what is a stoichiometric reaction. Yes, I can explain you shortly what is that, but I'm 100% sure you all know what is a stoichiometric reaction. Probably you might have studied in general chemistry. Stoichiometric reaction is something like if you say like 1 mole of A plus 1 mole of B giving rise to 1 mole of C. If you know the molecular weight of A, molecular weight of B, and if you imagine molecular weight of A is 10 gram, molecular weight of B is 20 gram, when we mix these two things up, the product mass should be equal to 30. That should be the molecular weight of your C. So that's how the stoichiometric reaction works simply. Okay, this is like try to explain it in only 1 minute, less than a minute. What's a stoichiometric reaction? But I don't want to go into the details, but that's the whole idea. So we are going to perform some stoichiometric reaction inside the batch reactor, and then in this compound C, we need to filter them from the rest of the solution. And then we are going to put some few more conditions. So we are going to assume something like a 95% conversion. 95% conversion in the reactor. So what do we mean by that? So 95% of your reactants are converted into products. So you have some 95% conversion here. Let me check what's the problem is. And few more conditions that we are going to define. So we cannot fill the reactor 100%, so we will fill the reactor only 90% of its volume. So 90% of its volume, 90% of its volume. And then we will put some flow rate to the heptane. So heptane we will pump into the reactor at some constant flow rate, something like 1200 liters per minute. So this is the amount of heptane that we are going to add into the reactor per minute. So that is we are going to pump them into the liquid, into the reactor, sorry. And then no, sorry, this is not correct. So we are going to load 1200 liters into the reactor at a rate of 30 liters per minute. So this 90% of this reactor volume, that's something roughly around 1200 liters of heptane. So we are going to pump 1200 liters of heptane into the reactor, but we are going to do that at some constant flow rate. So every 1 minute we are going to pump in 30 liters per minute. So roughly how many minutes we need to pump 1200? It will be like 1200 divided by 30. So 40 minutes we need to pump the 1200 liters into this reactor, into the batch reactor. So these are some conditions that we are going to keep. And then component A, we are going to feed 50 kg, and then component B, we are going to add 40 kgs. We're going to add 40 kgs. And then what else we need? And then we are going to put some conditions like at the end of your experiment we get some product C. So what we are going to tell to the software is like we are going to remove 100%. Whatever inside the reactor we are going to remove, filter them 100%. So no matter whatever the stream contains, this stream may contain some new product C plus your solvent, we are going to filter our product 100. We are going to remove everything inside the reactor, 100% of everything inside the reactor, and then we are going to pass them into the plate and frame filter. So that's second condition. Not second condition, that's one of the many conditions that we are going to consider while designing using the SuperproDesign software. So what we are going to do is like we will fill the reactor with A and B, and then we will take the product C out. So I hope you all understand. We can do 100% filtration, or we can do 95% filtration. So for the moment in the tutorial they have 95% filtration, I think. So let's filter, let's filter 95% of the product that comes out of the reactor using this plate and frame filter. Let's assume 5% is lost when we transfer some product from the reactor to the plate and frame filter. So that's a reasonable assumption. And then when you come back to, so we take a reactor and then we are going to filter 95% of everything that comes out of the reactor. And then in the filtration unit we are going to assume something like 35% we are going to lose during the drying. So you have some cake here, we will wash them and then eventually it will get dry. So during drying process, imagine if you have some cake, like a filtration cake, and if you have solvent inside the cake, so during drying process, the solvent will evaporate, and the solvent, during this evaporation process, the solvent will knock off some of the, will take some of the soluble components with it. So imagine if you start with the 10 kgs with that includes some of your solvent. So during drying process your solvent might take some of the components from your product material and then it will evaporate. So by that way we can assume 35% of your product is lost during drying process. So we can say like a cake dryness or loss due to or loss of your material during the drying may be something around 35%. So these are not assumption, these are something they state in the tutorial book. So I try to keep with those number. If you want we can even change, why not 25% or 10%. So what does that mean is like we have roughly 10% of soluble components in your product that will be soluble with your heptane and then it will evaporate with your solvent during the drying process. So that's the meaning of this thing. And then what else we have to remember, and then we are going to do something, we can call it as a process scheduling. You will study this in week 9 or 11 or 10, I don't remember. It depends how fast we are going to finish with other chapters. So process scheduling is something like so you have a reactor and then you have a plate and frame filter. So this reaction is going to happen for some time. I think I forgot to mention how long will be the reaction time. Let's check it out, 1 minute. Okay, the reaction time is around 6 hours here. So remember this is the batch process, so that's your reaction time. So once we add A and B, we are going to wait for 6 hours in order to get our product C in the reactor side. So that's what is happening. And then we are going to transfer something like 95% out, I said. So what is this process scheduling is all about? It's a very big term. I'll try to put it simple, only relevant to this particular example. So imagine you have some working in an industry, you have one unit. This is operating in a batch mode and this is operating in a batch mode. So what we are going to do now is like, so we are going to start this plate and frame filter only when the reaction gets completed, when the reaction is finished in unit 1. Unit 1 is our batch reactor. Yeah. So obviously we have something 6 hours of reaction time, and then filtration it will carry out, we will do filtration process for some amount of time. Let me check the time involved. Okay, filter. So reaction time is 3 hours and your filtration time is 3 hours. Filtration time is 3 hours. So the whole purpose of doing this process scheduling is something like we are going to fix the time, like this unit 2 we will start only when the reaction is finished in the reaction in the unit 1. So there will be some relationship between the starting time of unit 2 and the at the ending time or the batch how do you call the ending time of this batch process of unit 1. Yeah, so something like that. They call it as a master and slave relationship between these two units. So why do we call this as process scheduling? Is something like imagine the unit 1 we have 6 hours and then in filtration time we have 3 hours. So once we finished the filtration process, once we clean the filtration, we have a gap of roughly 2 hours, I think, if you put 1 hour to clean the plate and frame filters, and in that 1 hour if we can filter some other product from a third unit operation, say probably with a filtration time of 1 hour, so in that time we can use the same unit to filter other product that comes from another reactor. So that's how industries work. So they have only one, maybe like one reactor, one filtration unit, one drying unit, maybe 2 or 3 reactors, yeah, something like this, and then they have to effectively use the times of each of these unit operations, filtration unit, drying unit. So you finish the reaction 1, you use the filtration unit, take the filtered product out, clean the filter, and then if you have some time interval, you take the product from unit 3, filter it here, and then so on. So that's how the process scheduling works. It's a complex, it's not complex, it needs you need to know what you are doing about, you need to know the time involved in everything. It's not only the reaction time, the time also involved in the time you take to charge your reactants. In this case you are charging A and B, it will take some time. You are charging your solvent, it will take some 40 minutes if you set some flow rate of 30 liters per minute, and so on. And then after this we have a cleaning time, say like 30 minutes. So there are few other things involved, so we should know the time involved in almost every operations that we perform with each of these unit operations. Only then we can come to this stage of process scheduling. Yeah, but forget all these big details for the moment. For this tutorial, what we are going to do is like we have a reactor, we take the product out C, and then we are going to filter them, and then we are going to set a master and slave relationship. So how do we call the plate and frame filter as master, and we call this guy reactor as a slave. So what we'll do is like so the plate and frame filter, we will switch it on only at the end of the reaction which is happening in your reactor 1, yeah, or we can call it as unit operation or unit operation 1. So that's what we are going to set. So and then you will generate a Gantt chart. We will see them. So this Gantt chart will explain in one day how many times we can effectively use your reactor and then the filtration unit. So we will get this type of information in SuperproDesign software, and then this Gantt chart will also tell, like imagine if your reaction time starts from 0th minute and you get the dried product at the end of, say like just for example, say 17 hours. So it will tell every details. So how many minutes, say like 30 minutes to A, 40 minutes to B, 50 minutes to say like say if you have one more component, for example 60 minutes to charge your reactant C, something like that, and then your reaction time will go for 6 hours, and then your discharging time from the reactor to the filtration time, say it happened in say like 2 hours, something like that, and then your filtration time, say like 40 minutes, and then followed by drying time. and then yeah, it will give a general picture. So your batch process, it will be from around roughly here 6 hours plus the time involved in the charging of your fluids, so, or reactants. So it will give some nice information about the time factor involved. Like it will give every details, like even if you take some setup time to set up the reactor, say like 5 minutes to set up your reactor, everything ready, and also say like another 10 minutes of setup time to prepare, assemble everything together, and then say it takes say like 40 minutes to set up your filtration ready for the next batch process. So it will also take into account of the setup time and also your process time. So Gantt chart will explain everything. So in your assignment, what I'm going to give you is like a few examples, and then you need not few example, each group will solve some problem, and at the end of the day you have to create a Gantt chart, and then you are going to repeat whatever I'm going to do it now. So there will be something like a group project. So you do the project in group at the end of the, and then each of you should solve whatever I'm doing now right at the moment, but using a different number. So if I'm going to load with 40 kg, you can load your reactor with 80 kg of product B, and maybe 10 kg of product C, and then put some other, say like you're going put some conversion rate of 85 percentage, and then you can filter, instead of 95 percentage of your product, you can filter 100 percentage of everything that comes out of your reactor. So make your own assumptions, and then repeat the same example, and also attach this together with your report. So each of you will have, so how it works, like the group, you will have 4 members. You will solve the exercise which I'm going to give. So this is something like manufacturing of something some product, and then you finish this one, generate Gantt chart or any other chart that SuperproDesign software allows you to generate, and then you add the same example which we are doing now. You have to assume some mass for A, some mass for B, say 10 kg, 20 kgs, and then you filter say like 85 percentage of all the products, and then just assume during the filtration, instead of 35 percentage loss during drying, you can assume say 20 percentage or 5 percentage, why not, and then you take the product out, perform a mass balance operation, and then report a Gantt chart. So put your name in each of your name here. So member 1, your name. So your final report is going to be a bit bulky, yeah. So then you have to write what's the percentage you assumed for each of these values. So this one will take not more than 10 minutes for you, but for the exercise you have to work in group, you have to discuss with each other, and then try to make a nice report. So I hope, and then few more things I have to mention. So let's see, I think this is enough. I stated the problem, so I will stop recording of this video, and then I will start to record something directly on the software. So I will show how to solve this problem in the software, and then I think that's enough for this lab.